plague, poisonous trees, fentanyl. Dangers lurk around every corner of this world, and feeble humans like you and I are really just trying to survive. So to help us out in that mission, here's a compilation of some of the deadliest stuff on Earth to try to avoid. First up is Hank to tell us about exploding lakes in Cameroon. You heard me right.
In the evening of August 21st, 1986, 80 million cubic meters of carbon dioxide gas suddenly erupted from Lake Nyos in the West African country of Cameroon. This massive cloud expanded at 50 kilometers an hour, suffocating everything within a 25-kilometer radius, killing more than 1,700 people. The only known similar event happened at nearby Lake Manoon 2 years earlier, where 37 people died. And scientists weren't really sure at first what was going on. They figured these were some kind of volcanic eruptions because both lakes are close to Cameroon's Oku volcanic field, which includes 4 major volcanoes. But even though volcanoes were partly to blame for these explosions, it turns out that they were no volcanic eruptions. Instead, what made these lakes explode were limnic eruptions, which are like popping open the largest, most pressurized soda can of all time. The volcanoes near the lakes are a sign that there's magma or molten rock close beneath the surface. And magma releases huge volumes of carbon dioxide, which can filter up through the crust of the earth into the bottoms of the lakes. Now, these lake bottoms are highly pressurized and very cold, which is exactly what gases need in order to dissolve in water. So lots of carbon dioxide can dissolve in the lakes and just build up, sitting there. But as the CO2 continues to build, those lakes get to be like cans of soda pumped up with way too much fizz. Most lakes don't explode, thankfully, even if they're sitting on top of a whole lot of magma. That's because the water gets mixed around when the temperature changes throughout the year. In the fall and spring, the changing surface temperature affects the water's density and keeps it circulating, and in turn helps release the gas. But in Lake Nyos and Lake Manoon, things are very different. It's hot pretty much all the time, so the shallower, less dense water stays at the top of the lake, where the gas-infused deeper layers stay below. As a result, tens of millions of cubic meters of carbon dioxide can accumulate. No one's sure what exactly triggered Cameroon's limnic eruptions, but a seemingly minor event that another lake might not even notice, like a heavy rainfall or a landslide or a small earthquake, could send some of that gas-rich deep water up into the shallows. In which case, it's like poking a hole in that overpumped soda can and suddenly everything is covered in liquid and fizz. Except that instead of getting a little sticky, the liquid is a 25-meter wave of water and the fizz is a giant deadly cloud of carbon dioxide. For obvious reasons, no one wants this to happen again, so once scientists figured out what was going on, pipes were installed in the depths of Lake Nyos and Lake Manoon, allowing the carbon dioxide to escape before enough of it built up to cause another explosion. Now, though, there's concern about a third lake, Kivu, on the border of Rwanda in the Democratic Republic of Congo. It also has a lot of gas buildup, and the sediment at the bottom of the lake contains evidence of sudden lake-wide extinctions every few thousand years, probably because of limnic eruptions. Lake Kivu is extra dangerous, though, because it also contains enormous amounts of methane produced by bacteria that ingest the carbon dioxide. If that lake explodes, there could be both fiery explosions and widespread suffocation, and there are 2 million people living on the shores of Lake Kivu. So in 2011, plans were put into place to start siphoning off some of that methane and using it to generate electricity for Rwanda. The hope is that we can harness the terrifying power of limnic explosions before they can occur, maybe even put it to good use.
I definitely didn't expect exploding lakes, and allow me to add another unexpected item to your list of fears: giant clouds of deadly gas billowing through the sky. Here's the story of the deadliest smog cloud in history.
London is famously foggy. Sometimes that can mean a wistful stroll or another excuse for a cup of tea, but when fog mixes with smoke and chemicals produced by industry, it becomes something new: smog. And for a couple of centuries, London's smog could kill. Really bad smogs could kill 1,000 people in a few days, but no one did much about it until 1952, when a 5-day smog in London killed an estimated 12,000 people. It was called the Great Smog of London, and it helped wake up the country and the world to the dangers of unrestricted pollution. Fog is just a cloud that forms down here on the ground, which by itself isn't that bad. You might not be able to see well when you're driving. You might not be able to land your plane, but it's nice. But clouds can act like sponges, forming around and trapping whatever's already in the air. This wasn't the problem until the 1200s, when a lot of London switched from wood to coal for heating their homes. Burning coal creates soot and smoke, which can irritate your lungs, and also creates poisons like sulfur dioxide and carbon monoxide. Sulfur dioxide, which is a sulfur atom bonded to 2 oxygen atoms, reacts with water to form sulfuric acid, which can harm your internal organs, as you might imagine. And carbon monoxide, which is one carbon and one oxygen, binds with the hemoglobin in your blood to stop oxygen from getting around your body. So when London started burning coal, all the smoke and chemicals mixed with the natural fog, and it became thicker and darker as years passed. It wasn't a health crisis at first, but people did complain that the smoke smelled terrible. And this was back in the 1200s, when everything smelled terrible already. But it was easier to keep burning coal than to switch back to wood, so for centuries they just accepted the occasional thick, dark, smelly cloud hanging over the city. As you do. Things really got dangerous when the Industrial Revolution happened in the 1700s, because now coal wasn't just heating homes, it powered huge factories throughout the city, and all that extra smoke and soot made the air in London's fogs much darker. It became so common that a physician named Harold Antoine Deveau invented the term smog to describe it. Really smoggy days completely blacked out the center of the city so that you couldn't see more than a few meters ahead of you, even in the middle of the day. The soot also irritated people's lungs, causing illnesses like bronchitis to become more common. Some people even suffocated from breathing so much smoke or the poisons in the air. Individual smogs in 1873 and 1892 each killed over 1,000 humans and livestock, and we don't even know how many people died early from collecting soot in their lungs over the course of their lives. But coal kept London flourishing, so nobody did anything to stop it. Then came the Great Smog. On December 5th, 1952, a thick fog rolled in and mixed with London's dirty air, just like it did most winters. But this time, high-pressure weather systems surrounded London and kept the cloud from moving on. So an especially dense black smog stopped on London for 5 miserable days. The smog was so thick that flights were grounded, most public transportation was cancelled, trains collided, and theaters and movies stopped because people couldn't see what they were watching. This is difficult to imagine. This was 1952, not that long ago. An estimated 4,000 people died in those 5 awful days before the smog dissipated. A lot of them suffocated because their lungs were inflamed from breathing in so much soot. And with sulfur dioxide from the burning coal reacting with water vapor in the smog, Londoners also spent those 5 days breathing air full of sulfuric acid. That and the smoke contributed to respiratory and other health problems, which killed around another 8,000 people in the following months. Ultimately, roughly 1 in 1,000 Londoners died because of the Great Smog. Some people argued afterward that the spike in deaths was due to a flu epidemic, but scientists have investigated that in all sorts of ways, and it's really unlikely that the flu could have been anywhere near as devastating as the smog itself. 4 years later, Parliament finally passed a Clean Air Act that dictated what kinds of fuels could be burned within the city. It and other laws have helped rein in the smog problem in London, but even today, London's air pollution lowers the life expectancy of a lot of people and is indirectly linked to tens of thousands of early deaths every year throughout the United Kingdom. Despite the Great Smog's devastation, it took a while for other industrial powerhouses to take the hint. New York City had a series of smogs in the 1960s that affected more than 16 million people, and black, soot-filled rain coated Boston around the same time. But eventually, lawmakers around the world stepped in. Starting in the 1970s, laws got serious about limiting pollution, forcing car companies to make more efficient engines, and factories to produce fewer emissions. Because it turns out, turning air into poison, not a great idea.
So smog has killed 20,000 people. I see we're upping the ante. And really, the Great Smog sounds anything but great. The people who named it should have taken notes from the people who named killer bees. Here's Olivia with the story on those little buggers.
Over the last 60 years, a new type of bee has slowly been spreading north through the Americas. But these are no ordinary bees. They're killer bees. They'll come over to shake hands with their docile domestic honeybee neighbor, and the next thing you know, they've snuck inside, murdered the queen, and commandeered her workers. And once they've set up shop, they defend their hives with ruthless violence. Disturb a killer bee colony, and they'll attack by the thousands, pursuing their enemies relentlessly, raining down a hail of venom-laden stingers. But these bees were never even meant to exist. They're the result of a lab experiment that failed and then escaped. The real name of killer bees is Africanized honeybees, which comes from the fact that they're a hybrid of 2 subspecies, the European honeybee and the African honeybee. Africanized bees look almost exactly the same as European honeybees. Even bee scientists need to analyze their DNA to tell them apart. But they sure don't act the same. The hybrids were created in the mid-1950s by a Brazilian bee scientist named Warwick Kerr, a mad scientist bent on achieving world domination using an army of deadly insects. Well, actually, all he was trying to do was build a better bee for Brazil's honey industry. See, honeybees aren't native to the Americas. They come from Europe, parts of Asia, and Africa, and were brought here to produce honey and beeswax. While some honeybees have escaped and started feral colonies, they're essentially domestic livestock just like cows or chickens. And like any domestic species, humans selectively breed honeybees to enhance desirable traits like honey production or disease resistance. That's exactly what Kerr was doing. European honeybees are great at producing honey, but they weren't doing very well in Brazil. They were falling prey to disease and tropical predators. African honeybees, on the other hand, produce less honey, but are better adapted to hot climates like Brazil's, and are more disease-resistant. Kerr's goal in crossing the European and African honeybees was to breed a honeybee that could both flourish in tropical climates and produce plenty of honey. The only problem? African honeybees are much more serious about defending their nests than European honeybees. We're not totally sure why they evolved to be so fierce, but it might have to do with the vertebrate predators that evolved alongside them. These included humans, other primates, and honey badgers that were more than happy to raid their hives for honey and protein-rich baby bees. Honey badgers do what they want, and if what they want is to rip open your house and eat all your food and your larvae, you'd probably be pretty fierce too. But in Africa, beekeepers successfully keep and work with African honeybees because they know how to deal with their stronger defensive behavior. So crossing these bees with the European subspecies seemed like a promising idea. And Kerr's hybrid, the Africanized honeybees, did indeed fare better in Brazil's climate, and they had the potential to significantly increase honey production in the country. Problem was, they were still very aggressive. And then there was a small but legendary lab accident. One weekend in 1957, while Kerr was away, a visiting scientist accidentally released 26 of the hybrid queens from the experimental facility. Oops. The bees established colonies in the wild, interbred with feral European honeybees, and began to spread through South America. Eventually they reached Central America, Mexico, and the southwestern United States. This was very bad news for European honeybees because the Africanized bees compete for the same resources and win. They'll also happily murder the European queens and take over their hives. The hybrid bees did actually help increase Brazil's honey production, but now we have all these super aggressive hives in other places too. It's a weird case of one invasive species, or subspecies, I guess, replacing another. Except we really wanted the original European honeybees to stick around. But hysteria about these so-called killer bees didn't really get going until almost a decade after they escaped, when Kerr publicly criticized the military dictatorship governing Brazil at the time. In an attempt to discredit him, the government and some of the press started calling the Africanized bees Abelha assassina, or killer bees, and portrayed Kerr as a Dr. Frankenstein who had created bees that attacked people on command. Truth is, Africanized honeybees are only sometimes a threat. An individual bee is no more dangerous than a European honeybee. If you encountered one foraging on a flower, it would be no more likely to sting you. They're only more aggressive when defending their hive. And even if it did sting you, the venom in its stinger is essentially the same as the European honeybee. Unless you're allergic to bee stings, it takes about 1,000 stings to deliver a dose that would be lethal to the average adult human. The problem is that an Africanized honeybee colony is much more likely to sting you 1,000 times than a European honeybee colony. In the decades since they were created, Africanized bees have killed about 1,000 people, which translates to about 16 a year. The good news is, there's evidence that Africanized honeybees are starting to chill out. Information from beekeepers who work with Africanized honeybees in Mexico, as well as research on hives in Puerto Rico, suggests they're exhibiting less extreme defensive behavior. That might be because they've been interbreeding with the calmer European honeybees. But humans have also been exerting some artificial selection by destroying especially defensive hives. Still, you don't want to mess with any honeybee hive, unless you know what you're doing and have proper protective gear, even if it hasn't been taken over by the zombie apocalypse.
While killer bees have a scary name, the 1,000 or so people killed by these insects can't compare with the death toll that some other animals take, especially those linked with disease. So here's Stefan with an obligatory entry in this list: bats.
1/5 of all mammal species today are bats. And that's pretty awesome because they help us out in all sorts of ways. Like, they pollinate a lot of plants, help regrow forests and control pests, and their poop is a pretty excellent fertilizer. Plus, they're just really cool. Some of them can sense magnetic fields or use sound to find their food, and of course, there's one thing that they all have in common. They can truly fly. They're the only mammals around capable of powered flight, without the help of machines. But they're also somewhat notorious for something else, being flying sacks of germs. Now, you might have noticed that part, with all the talk about zoonotic diseases that's been happening lately. Those are diseases that are passed to humans from other animals. And while bats aren't to blame for everything, they have played a role in the transmission of at least 11 viruses, probably 12, counting SARS-CoV-2. These diseases aren't the bats' fault, of course. If anything, they're ours. Research shows that disturbing animal habitats is usually what causes the transfer of a zoonotic disease to humans. Still, bats in particular do carry a lot of viruses, and that's because they have unique immune systems, which means we can learn a lot about these pathogens and their effects by studying bats. In fact, bat immune systems are so special that what we learn from them could someday help us treat a wide variety of conditions, from cancer to diabetes. And the kicker is, bats probably have weird immune systems because they fly. Unlike gliding, flapping flight requires a huge amount of energy. So bats have evolved ways to kick their cellular fuel production into high gear, mainly by putting their mitochondria into overdrive. Those are special compartments within cells that turn food into fuel. But there's a catch. When mitochondria convert nutrients into energy, they also create byproducts called reactive oxygen species. So basically, mitochondrial exhaust fumes in the form of really reactive molecules which contain oxygen. Now, these aren't all bad. The immune system uses them to rouse immune cells to action and kill bacterial invaders. But they can also cause a lot of damage. They can weaken cell membranes, mess with proteins, and even break DNA. And because of that, they play an important role in diseases like cancer and arthritis. Cells can try to keep them in check with antioxidants, compounds that essentially neutralize these overeager molecules. But those can only do so much, and when the balance gets out of whack, cells experience a condition called oxidative stress. This is when most of the DNA damage happens. So bats' supercharged mitochondria mean extremely high levels of oxidative stress, which in turn means constantly high levels of DNA damage. But since bats don't immediately get super cancer after their maiden flight, researchers have long suspected that they've evolved ways to protect themselves from all this flight-related damage. And a few years ago, genetic studies found mutations which boost their ability to detect and repair damaged DNA. Essentially, they've also turbocharged the mechanisms that prevent genetically damaged cells from replicating, which may also explain why they don't seem to get cancers very often. So, bats produce tons of energy without damaging their cells. Sounds pretty awesome, really. But there's just one small problem. DNA damage can also be a sign of a viral infection, because viruses need to hijack the cell's genetic machinery to reproduce, and that process usually involves some strategic snipping. So naturally, DNA damage triggers an immune response, inflammation. Essentially, when cells detect DNA damage or other signs of infection, they chemically call in white blood cells. These cells kill and destroy pathogens using a variety of genetic and chemical tools. And they also help control how the inflammation unfolds, like by bringing in additional white blood cells or switching some of them from germ killing to tissue repair once the invasion is over. This immediate or acute inflammatory response helps to get rid of the invaders and promotes healing. But remember, thanks to their supercharged mitochondria, bat cells experience constant DNA damage. They can repair this damage thanks to those advanced DNA repair tools, but the damaged DNA should still light an immune flare before it's fixed. So bats would experience super inflammation all the time. And prolonged, chronic, and systemic inflammation isn't so great. White blood cells and the processes they set in motion can be really destructive to the body's own tissues. In short, too much inflammation can lead to organ failure and even death. So flight should be a death sentence. Except bats have evolved some neat ways to knock down inflammation too. For one thing, they dampen the activity of sting proteins. These proteins are one of the ways mammalian cells trigger an inflammation inflammatory response when a virus is detected. Also, a genetic analysis of multiple bat genomes showed that they're the only mammals that completely lack genes for pyhin proteins, another set of inflammation-triggering sensors activated by damaged DNA. And those are just part of the story. It will still be a while before we completely understand how bats prevent or dampen inflammation in their bodies, because it seems like every time they look, researchers keep finding more of these adaptations. So to recap, we know that to make sustained flight possible, bats have ramped up fuel production and DNA damage detection while dialing inflammation down to a 1. But we know that inflammation is one of the big ways the immune system fends off intruders, so doesn't that leave them open to all kinds of actual pathogens? And the answer is yes. Around the turn of the 21st century, scientists discovered that bats act as a reservoir for a lot of viruses that are extremely dangerous to humans. This includes filoviruses, which cause hemorrhagic fevers like Marburg or Ebola, and Henipaviruses like Hendra and Nipah, both of which can cause fatal brain infections. And of course, coronaviruses like SARS, MERS, and most likely the notorious new coronavirus that started the COVID-19 epidemic. And there's mounting evidence that bats were involved in transmitting these diseases to humans, either directly or indirectly, like by infecting farm animals. And bats are also suspected of having given us other diseases in the past, like mumps, measles, and hepatitis B. But here comes another magic thing about bats. Even though they're widely infected with notoriously deadly viruses, they don't actually seem to get sick from them. The virus can be found in their bodies, but they don't have any symptoms. As for how that's possible, well, we still have more questions than answers, but researchers have discovered a few evolutionary quirks about bat immune systems that help make that happen. In part, that's because active viral infections in bats tend to be pretty short-lived, thanks to their hypervigilant interferon production systems. Remember how we said DNA damage is a signal of infection? That's because viruses try to reprogram cells to create copies of themselves. But cells aren't sitting ducks during this process. In addition to calling out for help, which is that whole inflammation bit we discussed, cells have an internal defense mechanism. They can make a protein called interferon alpha, which activates genetic and chemical tools that reduce the virus's ability to multiply and spread. Every other mammal we know of switches their interferon system on when an infection occurs. But genomic studies suggest bat cells always have their interferon alpha genes activated. This drastically cuts down the time it takes to react when a virus is present, so it allows bats to nip the infection in the bud before it becomes a full-blown disease. And of course, there's more. All mammalian cells contain an enzyme called ribonuclease L, which when activated chops up viral RNA to stop a pathogen from spreading. But in us and most other mammals, activating this enzyme takes a complex chain of steps, so it's not super quick. But bats, on the other hand, can activate it directly with interferons, drastically speeding up infection containment. Scientists also think this fast activation of ribonuclease L helps bats outsmart viruses that have evolved to inhibit the enzyme before it can be switched on, something HIV does in humans, for example. So basically, when bats do get viruses, they're able to quickly clear them out, for the most part. They can still fall prey to at least a few, like the rabies virus. And even quick suppression of a virus can mean it stays around in a group of bats. Bats tend to huddle close together when they roost. Plus, they fly around in the same areas as bats from other colonies, and they're constantly spraying snot and saliva everywhere when they echolocate. So there's a good chance that during that window when a bat has a virus that is actively replicating, it will spread it to another bat. That means that even if each bat only hosts a virus for a short time, it can linger in the population. And even this probably isn't the full picture. Mathematical models indicate that by themselves, bats' social habits don't completely explain why they host so many viruses. Instead, research suggests that the viruses themselves have figured out how to lie dormant and undiscovered, like in the bat's lungs, spleens, or intestines. And then when the bat gets stressed, like when it's roused from hibernation, that stress temporarily dampens its antivirus systems, allowing any hidden viruses to emerge. This leads to another period of increased viral replication and shedding, so again, the bat can transfer the infection to other animals. Then its antiviral systems get back up to speed, and the viruses are eliminated or driven back into hiding. Still, even when a virus is replicating and being shed, bats don't generally seem sick, not like a person would with the same virus. And that's likely because their inflammation dampeners are still running. So they're still suppressing a lot of the immune responses that would make them noticeably sick. And that may also be why viruses that are deadly to us aren't lethal to them. It turns out that the most severe symptoms of illnesses like MERS and Ebola, the symptoms usually responsible for their lethality, aren't caused by what the virus itself does to the body. Instead, they're the result of the destructive, catastrophic inflammation the virus triggers. This includes an extreme systemic reaction called a cytokine storm, where an over-release of pro-inflammatory signaling proteins turns a person's own immune system into their worst enemy. And some researchers think that our aggravated inflammatory response may actually be because these viruses have evolved to dodge the super-refined immune systems of bats. Basically, they evolved to survive in a host that constantly and aggressively attacks their ability to replicate. So when that assault is suddenly weaker in a new host, they go wild and produce a lot of little virus babies that send the host's immune system into panic mode. This kind of overreaction can also happen to bats, it's just not usually in response to viruses. Instead, it seems like their unique immune system may leave them vulnerable to non-viral invaders. The most infamous example of this is white nose syndrome, a fungal pathogen which has devastated bat populations in North America. Some researchers think the bat's dampening of inflammation, especially during hibernation, makes it easy for the fungus to infect the bat. Then, once the bat awakes, its immune system does react, only it goes too far, which can lead to the bat developing a life-threatening form of systemic inflammation. So basically, the reason they die from white nose is similar to why we die from viruses like MERS and Ebola. That may mean that the key to saving bats from this fungus, and us from the deadly viruses they carry, may lie in further research on bats. And also, if we're being selfish, we have a lot of other diseases characterized by inflammation, like heart disease and diabetes. So studying their inflammation system may lead to treatments for our chronic conditions. And the same goes for studies on the ways that bats keep viruses at bay. Right now, we only have effective antiviral drugs for about 10 of the more than 200 viruses that can infect humans, and very few broad-spectrum antivirals. If we can discover more of bats' tricks, we might be able to use them to develop therapies against the diseases they host and other dangerous viruses. Plus, all this research might help us live longer. Many researchers think bats' immunological adaptations are also behind some of their other superpowers, like how they seem to rarely get cancer, or how they live incredibly long lives for animals of their size. Usually, little animals live fast and die young, but Brandt's bats can live for over 40 years, even though they only weigh 4 to 8 grams. So instead of looking at bats as species zero, we should think of them as flying keys to longevity and resilience. And in the end, they're going to be our allies in health, not our enemies.
Now that we've broached the subject of infectious disease, we have to mention the 1918 pandemic, aka the deadliest flu in history. Here's how it killed up to 100 million people.
By now, you're probably used to flu season coming around every year. These days, you can often avoid getting sick through vaccines, washing your hands, and avoiding sneezing coworkers. So while influenza can be dangerous, for most people, it's just another part of winter. But 100 years ago, at the start of 1918, the normal flu season took a backseat to what became the deadliest outbreak in history. A global influenza pandemic that killed anywhere between 50 and 100 million people. Today, it's called the mother of all pandemics. Epidemiologists still aren't sure where this killer flu originated. Some say it started in China, while others point to early cases from a military training base in Kansas. But eventually, thanks to the war and global trade routes, it spread around the world and became known as, of all things, the Spanish flu. See, in 1918, a lot of the world was busy finishing World War I, and many countries were heavily censoring their news. Anything that might hurt morale, like a deadly, fast-moving plague, for example, was kept from the media. But Spain, which wasn't involved in the war, had no problem reporting the outbreak. So people started calling it the Spanish flu, since it seemed to have emerged there first, if only according to the news. Regardless of where it started, this flu was so devastating that some people believed it was biological warfare. Some estimates say that 1/3 of the world population was infected, and that more than 2.5% of people died from it, often through complications like pneumonia, including millions of 20 to 40-year-olds, who are usually the least vulnerable. A normal flu, meanwhile, is fatal in less than 0.1% of cases. To know why it was so dangerous, it helps to know a bit about the flu virus itself. There are 4 subtypes of the influenza virus, called influenza A through D, with influenza A being the main kind that causes pandemics. Those viruses are categorized by 2 surface proteins, hemagglutinin, which comes in 18 varieties, and neuraminidase, which comes in 11. They give flu strains names like 1918's H1N1, although there can still be variations among viruses with the same name. Your immune system builds antibodies that recognize all these proteins and protect you from multiple infections. But unfortunately, the influenza virus mutates so quickly that your body doesn't always recognize it. Most mutations are small, enough that your body will probably still be able to defend itself. These tiny changes are called antigenic drifts. But the 1918 flu virus underwent a much bigger change, called an antigenic shift, that left people vulnerable. These big mutations result in viruses with very different or entirely new combinations of surface proteins. And they're different enough that most people have little or no natural immunity. Changes like these are what cause flu pandemics. Now, even though the virus changes all the time, scientists think that the first flu you encounter may have a lifelong effect on the way your body fights new infections. They call this idea the antigenic imprinting, or the doctrine of original antigenic sin. Really. It says that your immune system seems to remember your first influenza infection and will try to fight later flus using the same antibodies. So, if you caught an H3 type flu as a child, you're better able to protect yourself against other H3 flu viruses, even if some of its other proteins have changed. But you probably wouldn't do as well against, say, an H1 type virus, which is exactly what happened 100 years ago. And it's one reason why 20 to 40-year-olds were so likely to die during this outbreak, even though they're usually the least affected. When they were younger, the so-called Russian flu was the dominant strain, and that was probably the H3N8 variant. Then, around 1900, the H1 type virus became dominant. And sometime right before 1918, another shift created the H1N1 strain that caused the pandemic and left young adults with almost no immunity. Meanwhile, people older than 40 may have experienced an H1 type virus in their childhood, so they already had some protection against this new version. On top of that, young adults also have especially strong immune systems, which actually worked against them and caused a lot of people to die quickly after showing symptoms. These rapid deaths were likely caused by cytokine storms, which is an immune system response so intense it damages a patient's tissues. And the stronger your immune system, the more damage a cytokine storm can do. So 1918 was not a great time to be a young person. After racing across the world, the deadly pandemic seemed to burn itself out after a year or so. Researchers think that since so many people were infected in the first outbreak, enough of the population gained immunity to prevent further chaos. The virus also probably mutated to a less deadly form, though in general, scientists aren't certain what magical combination of mutations makes a flu more or less deadly. Either way, we don't need to worry specifically about the Spanish flu these days. Many of today's H1 viruses are actually descended from that 1918 virus, which is partially why it's called the mother of all pandemics. So most people have some H1 immunity. But if there's ever another big antigenic shift, that could be a problem, because it could definitely happen and might even cause another pandemic. To protect us from that possibility and the rest of the flus, scientists are working on a universal vaccine. There are several in development right now that target parts of the virus that are the same across all variants. And if any of them work, it could someday mean that one vaccine could protect you from every flu season. So even though it's possible, hopefully we'll never experience another pandemic like the Spanish flu again.
The ending of that video didn't age well, but even though pandemics continue to occur, none of them compare to the plague of the 14th century. Remember that? You should, because it's still at large.
In the 14th century, the Black Death spread throughout the Old World, wiping out somewhere between a quarter and half of all the people living in Eurasia at the time. And that put the plague right up there with smallpox as one of the deadliest diseases our species has ever faced. But of course, nobody gets smallpox anymore. Literally nobody. It's been eradicated. You would think the Black Death is one of those diseases left in the dustbin of history too. But the plague is alive and well, and while it's not causing world-changing epidemics anymore, it's still a problem. It turns out we're still learning a lot about this infamous bacterium, and the new intel might help scientists determine if it will ever go all medieval on us again. The plague is caused by the bacterium Yersinia pestis. It evolved from a mild gut bug sometime in the last 10,000 years, and it's been plaguing us since at least 541 CE, when it picked up a mutated version of a gene called PLA, a protein-cutting enzyme that allowed it to infect more of the body and spread more virulently than its older cousin. Now, there are actually 3 types of plague. Bubonic plague is when it infects the lymph nodes, causing them to swell up as painful buboes. If the infection spreads to the bloodstream, it becomes septicemic plague. But the form of most concern to public health professionals is pneumonic plague, which is when it infects the respiratory tract. It's more deadly than the other forms, and it can easily spread from person to person directly because infected people send bacteria-filled droplets into the air when they cough. And that's a big deal because usually the bacteria move around thanks to the help of other critters, called vectors. The plague is a zoonotic disease, meaning it can spread between humans and animals. And while rats are usually blamed for the spread of plague, the actual vectors are biting parasites like fleas, which carry the bacteria in their guts. In fact, a study in January of 2018 suggested that the fleas and lice which spread the Black Death may have mostly been dining on humans rather than frequently jumping between rodents and people. But rodents can get the plague and act as carriers, meaning it can hide in their population while it's not infecting us. Something that definitely did happen back then and still happens now. Fortunately, all forms of the plague are treatable with antibiotics. The challenge is catching it in time, since its early symptoms often resemble the flu. And doctors, well, when they see flu-like symptoms, they guess flu before they guess the actual literal plague. So could the plague ever mount a Michael Jordan-style comeback? Well, for people in some parts of the world, back is the wrong word. The plague is native to parts of North and South America, Africa, and Asia. And though it isn't wiping out a third of the world's population like it used to, it does still cause serious outbreaks in places like Madagascar. And there are a couple thousand cases reported every year. And that's in part because of those furry carriers. It's neither feasible nor desirable to wipe out all the animal reservoirs the plague can hide in, like rats and ferrets and cute little kitties. And unlike with smallpox, good plague vaccines don't exist. At least one promising one is in development, but prior to that, existing vaccines could cause nasty reactions, had to be re-upped frequently, and they didn't really work very well anyway. A real triple crown. Even today, scientists are still unlocking the plague's nasty little secrets. It wasn't until 2015 that a study published in PLOS Pathogens described how the bacterium could make its way from a tiny shallow flea bite to your lymph nodes. Since it's still around, the short answer is yes, the plague could rise again. Luckily, modern hygiene and clinical practices generally keep it in check. We're usually able to get anyone who's coughing up plague-laced sputum off the street before they encounter too many other people. So person-to-person transmission has become blessedly rare, and we don't tend to interact so much with flea-infested animals. But the real game changer has been those antibiotics. And that's where the potential for a modern outbreak becomes a little more of a reality. See, in 1995, researchers raised red flags over the discovery of strains of the plague that were resistant to some antibiotics, which would make for an extremely deadly outbreak and is therefore a perfectly reasonable thing to raise red flags over. However, these drug-resistant strains haven't caused much trouble yet. That's partially because it actually seems to be difficult for the plague bacterium to acquire antibiotic resistance. Drug resistance is often transmitted among bacteria on small circular snippets of DNA called plasmids. Plague bacteria have to pick up these resistance-conferring plasmids from another bacteria, but they just don't seem to run into resistant bugs that often in nature. And unlike humans, rodent populations don't frequently encounter antibiotics. So there doesn't seem to be an evolutionary advantage ensuring that the plague bacteria will hang on to drug resistance even if they do pick it up. But if there was to be a global pandemic, it would most likely be from a resistant strain, or from one modified for bioterrorism. There's actually a really long history of using the plague as a weapon. Armies used to catapult corpses over the walls during sieges to help thin the defenses. But doctors, scientists, and military personnel have plans in place in case anyone does try to modernize that strategy. And anyone who would even consider such a thing would be violating several international agreements. Short of these two scenarios, a 21st century Black Death-like epidemic is pretty unlikely. That doesn't mean the plague isn't a problem for the thousands of people who do catch it every year, but fortunately, by developing better vaccines and continuing to study the bacterium responsible, we're working on beating it back for good.
A drug-resistant version of the plague is a whole new kind of scary. Like, we don't need to help it become more deadly. But that's just one example of how humans might create the deadliest things on Earth. Another very real example of that is fentanyl. Here's Reed to explain how it became such an efficient killer.
With the current opioid overdose epidemic, there has been a lot of discussion about fentanyl. It seemed to pop up kind of out of nowhere and has been a major cause of the increase in overdose deaths since about 2012. And it turns out that's not just a coincidence. Fentanyl is especially deadly because of the specific chemistry of the compound and the tendency for people who use it illicitly not to know how much they're taking at once. So in the ongoing fight to reduce opioid overdoses, we need to understand as much as as we can about the specific threat of fentanyl and how we can keep people safe from the dangers it poses. To be clear, the fentanyl that's causing so many overdose deaths is illicit fentanyl, which is the kind that is made illegally and not regulated. But to start, let's explain exactly what the drug is. Fentanyl is an opioid, which is a type of painkiller. It's in the same class of compounds as opium, morphine, or heroin, but fentanyl is very strong, something between 50 and 400 times stronger than morphine. These drugs are also sometimes called narcotics, but for this video, we're sticking with the term opioid. Opioids mainly block pain by binding to something called mu-opioid receptors. These are basically small molecular switches on our nerve cells. Activating these receptors tweaks how easily and how often our nerve cells send electrical signals. Imagine them kind of like volume knobs on your nerves. Activating the receptor essentially turns the volume down. The end result is that the cells are less responsive to stimulation. Less response equals fewer pain signals equals less pain. And this is often what we want these drugs to do. Opioids have been used in medicine for a long time. Even fentanyl has been used as a medicine for decades. It was first introduced to the market in the 1960s as an anesthetic. Chemists had been looking for new painkillers that were stronger, safer, and with fewer side effects than previous ones like morphine. One of the ideas was to look for compounds that could dissolve into fat better. The thinking being that this would help them get into the fat-rich central nervous system more quickly. And out of that research came fentanyl. Fentanyl wasn't used all that much until the 90s though, when there was a breakthrough in the ways that it could be administered that made it more appealing clinically. It's still used today for things like surgery, and chronic pain patients can get it in patches or lozenges to help with pain management. But like any incorrectly used opioid, fentanyl's effects on the central nervous system, the ability to turn down the volume knob on our nerve cells, can be dangerous. Opioids can also slow down respiration, since it turns out the same receptor that blocks pain is also found in the cells in the brainstem that control breathing rhythms. The whole process is complex and still being studied, but it looks like opioids also make these cells less responsive to electrical stimulation, slowing down your breathing. And if you keep turning down the volume, well, eventually, you'll get to no sound at all. What's more, opioids can also tamp down a second breathing reflex we have to get rid of excess carbon dioxide in our blood. This kind of 1-2 punch means that if you take too much at once, a person can be in real danger of suffocating. That said, doctors are aware of this danger and keep it in mind when they write fentanyl prescriptions. The problems come into play when fentanyl is used illicitly or without the supervision of a medical professional. It's also only dangerous if it gets into your bloodstream. You can't overdose just from touching or being near fentanyl or any other opioids, despite what you might have heard elsewhere. And to be clear, all opioids have their dangers, not just fentanyl. But fentanyl is particularly dangerous because it's so much stronger, meaning the dose needed to overdose is much less than for other opioids. Experts say that as little as 2 milligrams of fentanyl, which is about 1/10 of the weight of a penny, can be enough for a lethal overdose. As for why you need so little to get the same punch as other drugs, it comes down to 2 key factors. Fentanyl works fast, and it binds to your mu-opioid receptors in a weird way. First up, it's speed. Remember how we said that fentanyl was created because scientists were looking for something good at getting into the fatty tissues of the nervous system? Yeah, fentanyl's what's known as strongly lipophilic, meaning it dissolves well into fats and oils. Because of this, it can quickly cross the lipid-rich blood-brain barrier, a kind of biological shield that usually slows down or stops drugs from getting to the brain. That means that fentanyl can just straight up get to the receptors faster than morphine can. Again, that's good if you're a doctor looking for fast-acting pain relief, but in an overdose situation, that means that breathing problems start sooner. This might mean that a person overdosing, or even someone nearby, might have less time to realize that something's wrong before things get dangerous. Which brings us to the binding. Fentanyl seems to bond to those mu-opioid receptors differently than other opioids do. And it may come down to the shape of the molecule itself. Morphine, for example, is kind of short and squat, but fentanyl is long and skinny. Both of these opioids fit into the receptor itself, which is how they bond there. Based on computer simulations, we think fentanyl forms a different kind of chemical bond that seems to activate the receptor more strongly. What's more, fentanyl's long, skinny tail also unlocks and interacts with a second, deeper pocket in the receptor that morphine can't reach. We're still learning exactly why these different bonds result in different potencies. Like, we still don't know what mechanically is changing in there between the two drugs. And it's worth noting that fentanyl can also affect other receptors on the cells too. So the story might not just be about mu receptors. But all in all, it seems to translate into a bigger response from the cell. So basically, it's kind of like the difference between tapping the volume down button once and really hammering on it. So is there anything we can do to prevent or decrease overdoses of fentanyl? Yes, but it may be difficult, and these ideas often ultimately start to get into questions of public policy rather than public health alone, since that may mean addressing some of the social or medical issues that lead people to start using drugs like fentanyl. Unfortunately, going into the specifics of how to fix a major societal problem is a little beyond the scope of today's episode, and maybe the scope of the whole channel. But we do have methods of mitigation that have been extensively researched, so we can talk about which potential solutions have scientific data to back them up. A lot of these are what's known as harm reduction strategies. In essence, not how to prevent addiction in the first place or how to address it long term, but what we can do to limit the harm and keep people as safe as possible if they are using drugs. Because preventing overdose deaths means saving lives, which is always a good thing. For starters, it's vital to make sure that people are getting the medical care that they need. If doctors are able to treat people for their health issues like chronic pain, people are less likely to turn to illicit use of opioids to self-medicate. As one example, there are still pervasive racial disparities between who gets prescribed a treatment for their chronic pain. Black patients are less likely to be given a prescription opioid to treat chronic pain than white patients. Pain management under the supervision of a doctor is critical for everyone. Because when people in pain can't get a prescription medication to treat their pain, but can easily access illicit street drugs, it's no wonder that they'd take that option. Part of avoiding fentanyl overdoses may also be helping people know if they're taking fentanyl in the first place. See, a lot of overdoses happen when someone thinks they're taking a drug of a lower potency, but their drugs were tainted or spiked with fentanyl, which means they were essentially tricked into taking fentanyl and don't modify the dose to reflect how much stronger that compound actually is. So we can prevent a lot of overdoses if we give people resources to screen their drugs for contamination. For example, fentanyl test strips are a quick and accurate way to test if a substance contains even a trace amount of fentanyl, and they're relatively cheap to make and distribute too. Another option for harm reduction may be opening what's known as safe injection sites. The idea behind safe injection sites is that people who inject drugs are allowed to do so while supervised by medical staff, who are trained to intervene in the event of an overdose. It may sound like an outlandish idea, but safe injection sites have been around for a long time. The first safe injection site in North America opened in Vancouver in 2003, and after it opened, the fatal drug overdose rate in its vicinity dropped by 35%. And it's not just that one site. A systematic review from 2021 found that other facilities were associated with significantly fewer overdoses and fewer deaths from overdoses and improved access to treatment programs. These are just one of many interventions aimed at preventing overdose deaths from all manner of drugs. And while not all fentanyl is injected, these sites can also offer fentanyl testing strips and other safety precautions. Not only that, but we can even reverse overdoses after they happen, using a medication called naloxone. It's what's called a receptor antagonist, which means that it also binds to mu opioid receptors, but doesn't actually activate them. All it does is physically block other opioids from binding to the receptors. Naloxone can be given via needle or nasal spray and can restore someone back to normal breathing within a couple minutes. But fentanyl's potency and speed means that the window for someone to either administer naloxone or call emergency services is much smaller than with other opioids. There's been a proof of concept study into a wearable injected device that could detect an overdose and automatically administer naloxone. It would activate when a significant decrease in heart rate was detected. And while getting a device like this out into the real world would no doubt be complicated, We wanted to include it to show that there are a lot of folks approaching harm reduction from a lot of different angles. So that's the deal with fentanyl. It's an opioid painkiller. It's a drug, and like many drugs, it does have legitimate uses, but it can also be addictive. Its particular chemistry gives it speed and power that most other opioids don't have, and all that spells trouble. Researchers hope that a better understanding of how fentanyl works at the cellular level will help prevent future overdoses.
Fentanyl became a killer after we made it and gave it to people, but something like asbestos is kind of a combination between a natural and human-made killer. It's a rock. It doesn't get much more natural than that, but people die from it when they spin it into yarn and stuff. Here's how asbestos made it onto this list.
4,500 years ago, Finnish pottery makers discovered a stone made of thin fibers that mixed really well with the clay they used to make pots. This peculiar stone was so strong and yet flexible that they could use it to make their pots thinner and bigger than ever. Plus, it was surprisingly resistant to heat, so the pots could hold things like hot metal. It seemed like something of a miracle stone, and eventually the ancient Greeks and Romans and Egyptians all started using it too. That rock was what we now call asbestos, and eventually we found out that it was too good to be true and stopped using it so much, but that took a pretty long time. The word asbestos actually refers to 6 different minerals that all have the same habit, or way their crystals grow. They're called asbestiform, which just means that they grow in long, thin, flexible fibers. That flexibility, plus their strength and resistance to damage by heat and harsh chemicals, made these minerals incredibly useful in industry. The problem, of course, is that inhaling asbestos fibers can be dangerous because to your lungs, those flexible fibers are more like sharp little knives. You can probably imagine what happens if you breathe them in. They get stuck in the mucus lining of your lungs, which can make it difficult to breathe. Inhale too many of the shards over time and they cause diseases like asbestosis, or scarring of the lungs, and mesothelioma, a type of lung cancer. The forms of asbestos with the highest health risks are part of a group of rocks called amphiboles, and what makes them cause more health issues than others comes down to 4 of their chemical and structural properties. First, amphibole fibers are smaller, so they can travel deeper into the lungs. They're also sharper, so they can pierce your lungs more easily, causing inflammation or creating scar tissue. Plus, they're hydrophobic, or water avoiding, which can keep them from dissolving in mucus. If they dissolved, they could get coughed up and get out of your system. Finally, they contain iron, which can react with oxygen in your lungs and damage the DNA in your lung cells. The damaged DNA can then make the cells divide too quickly, leading to a tumor. So they may be more carcinogenic or cancer-forming as well. So how did asbestos go from being the miracle rock of ancient potters to the scourge of modern industry? Well, even as far back as the Roman Empire some 2,000 years ago, historians wrote about slaves getting what they called a sickness of the lungs after working in asbestos mines. And when the first commercial asbestos mines opened in Quebec in 1879, asbestos-related health issues started showing up in medical journals and case reports. One of the first well-studied deaths was in 1924 in the UK. Nellie Kershaw, who'd been spinning asbestos into yarn since she was 13, died at the age of 33 from asbestosis. When Parliament heard about the case, they asked a doctor known as E.R.A. Meriwether to investigate the health of asbestos workers. For 2 years, he studied 374 workers at an asbestos textile factory. He found that inhaling asbestos fibers caused scarring in the lungs, and 17 out of 20 workers who had been there for more than 20 years ended up with asbestosis. Meriwether presented his paper to Parliament in 1930, and the UK started requiring ventilation in asbestos factories a year later. But it wasn't until 2003 that asbestos was banned throughout the European Union. The asbestos industry in the United States is a whole other story. Asbestos was used a whole lot during World War II since it was cheap, strong, and resistant to fire and chemicals. Naval warships used asbestos insulation, and buildings were constructed with asbestos floor tiles and shingles, cements, and insulation for pipes. Production of asbestos in the US finally started to slow down in 1979 when 9 asbestos manufacturers filed a lawsuit against the federal government. In 1975, they'd paid $69,000 to an asbestos worker who'd developed asbestosis, and they wanted to be reimbursed. But the government wasn't having any of that. Instead, they proved that the companies knew about and had been hiding asbestos-related health information for decades. The case got a lot of media attention, and people started to try to fix the problem by removing asbestos from buildings, but the US still hasn't entirely banned the use of asbestos. Even so, asbestos won't cause health issues for most people. Most of the fibers are so tightly bound into another material that they won't escape into the air unless you're trying to remove the asbestos. Plus, every year, we and everyone else on Earth breathe about 1 million fibers just from the natural erosion of asbestos-containing rocks. So unless you're an asbestos worker who spent a lot of years without a ventilation mask, or you're an ancient Finnish potter, you probably don't have to worry about getting an asbestos-related illness anymore.
So asbestos is a nasty character, but the simple act of touching it in rock form probably isn't gonna hurt you. I wish I could say the same for the little apple of death tree. Here's Michael to explain more.
If you're ever vacationing in the Flamingo section of Everglades National Park in Florida, beware of the apples. In fact, if you're pretty much anywhere from northern South America to Florida, including the Caribbean and Galapagos Islands, and you see a tall tree growing near water with yellowish, greenish, crabapple-looking fruit, it's probably best to keep your distance. The fruit might be delicious, but it could also be deadly. Because that tree might be a manchineel, which, according to the folks at Guinness World Records, is the world's most dangerous tree. Every part of the manchineel is toxic. The sap in its wood and leaves can cause blindness and blistering. Its fruit can cause boils in the mouth and throat, as well as severe intestinal damage that can kill you. It's no wonder Spaniards gave it the nickname La Manzanilla de la Muerte, or Little Apple of Death. The tree contains a number of toxins, but the worst is probably forbol, or should I say forbols. Forbol refers to a family of related organic molecules that have two terpene chemical groups, and they're similar to compounds you have in your body, which is a bit of a problem. See, forbols mimic the action of diacylglycerol, a fatty molecule your body uses in a number of ways, including to activate an enzyme called protein kinase C, or PKC for short. PKC is a pretty big deal because it regulates things like cell growth and metabolic activity. So when forbols overactivate PKC, cells will increase their expression of genes involved in inflammation and cell death. This leads to a range of nasty effects like blistering and ulcering. Manchineels have forbols everywhere, which is why you shouldn't touch any part of them. Oh, and here's a not-so-fun fact. Forbols are very soluble in water, so it's not a good idea to stand under a manchineel when it's raining either, which, you know, it does in places like the Everglades. A lot. What's not entirely clear is why this tree went so overkill on the toxicity. It may be that since the manchineel typically grows in areas where there are lots of other toxic plants, it has such overdeveloped defense mechanisms to stay competitive. And it can get away with having toxic fruit because it doesn't need animals to spread its seeds. It lives by the ocean, so its fruit can bob along on the waves to move to new lands. Though it may get more love from critters than you'd think. Some reptiles seem to eat the fruit with no ill effects, and black spiny-tailed iguanas will even live in the trees. How remains a mystery. And even our species doesn't always keep away. Because the trees live in places like Florida, where there are lots of strong winds, and hurricanes every so often, their wood is really hard. So cabinet makers love it, though they have to carefully cut and dry the planks for several days to let the forbol-laced sap evaporate out. And the trees aren't just hard. Their deep roots and thick branches help protect coastlines from damaging winds and waves. That means, while they might be toxic to touch, they help protect us and coastal ecosystems during storms. So if you do see a manchineel while you're strolling along the beach, you can smile and appreciate all it's doing for the plants, animals, and people who live nearby, and then give it a wide berth.
I feel like we can make cabinets out of less deadly stuff. Come on, people. Let's just stay away from deadly apples. For that matter, let's stay away from all the food that kills us. Here's how we know what to put on that list.
I think we can all agree that food is pretty great. So participating in an experiment where almost all you have to do is eat 3 delicious meals every day for up to a year sounds kinda like the dream. But imagine knowing that hidden in one of the foods, maybe the butter, maybe the freshly picked peas, is a substance that's probably toxic. It sounds unthinkable today, but that was the setup of some of the strangest and most infamous human experiments in American history, known as the poison squads. They ran for 5 years starting in 1902, and even though they wouldn't pass any scientific ethics committee today, they were revolutionary at the time because people started to realize that maybe they should make sure the things are safe to eat before eating them. The trials were the brainchild of Harvey Washington Wiley, the head chemist with the US Department of Agriculture. Back then, food additives didn't have to be tested or even put on the labels, and he wasn't really okay with the idea that no one in America had any way of knowing what they were actually eating unless they had grown or raised it themselves. Formaldehyde, for example, regularly popped up in milk to keep it from souring. Yeah, the known carcinogen that we use to preserve dead bodies. And you'd also often find borax, a mineral that contains sodium and boron, in meat. It made the meat firmer, which made it seem fresher, especially when combined with an extra pinch of salt and red food coloring. These days, borax is a common ingredient in things like detergent and pesticides. And we're not talking tiny, insignificant amounts of this stuff either. But no one had bothered to investigate whether these additives were actually safe to eat. So with $5,000 from the government, Wiley hired a chef, promised a bunch of otherwise great free food, and recruited a dozen healthy young men as volunteers. He took their weight and vitals, made them collect their urine and feces, and gave them weekly physicals. Then they started with a low dose of a specific chemical and went up, stopping only when the men were too sick to continue. The first poison squad tackled borax and its derivative boric acid, because they were so common. At first, the chef hid the chemicals in butter or milk, but the volunteers could taste the metallic flavor and instinctively avoided it, because no one wants to eat butter that tastes like their silverware. Wiley still needed the men to get the right dosage, so he just put the borax in pills for them to pop about halfway through their meals. Bon appetit. The guys on the poison squad reported stomach pains and feeling less hungry when they were fed 2 to 3 grams of borax a day. At 4 grams, they became very tired, developed headaches, and couldn't work normally, which sounds like an average Monday to me, but apparently in their case it was caused by the borax. Through other trials, Wiley also found that if they took a lower dose of half a gram a day for long enough, they'd get similar symptoms. Today, we know that eating borax can cause tissue damage, which can eventually lead to fun things like vomiting and convulsions. So thanks for saving us from that one, Poison Squad. Thankfully though, almost no one walked away from these experiments with any obvious long-term problems. Wiley also tested copper sulfate, which was added to things like canned peas to make them bright green, as well as formaldehyde, sodium benzoate, and salicylic acid. And while the effects on the men varied, Wiley concluded that none of the additives were safe. Today, any scientist looking back at these trials would be horrified by not only the ethical problems, because giving people potentially deadly substances, even if they know about them, is never okay, but also the poor experimental design. For one thing, the participants knew they were eating a potential poison, which could have easily skewed the symptoms they reported and made them feel more sick than they actually were. Not to mention that for the most part, the experiment had no real control group. In between testing each substance, the squads were given a break for several weeks, but they weren't asked to continue reporting symptoms or to keep collecting their urine or fecal samples. You also can't really conclude much from a small and specific group of people. Wiley thought that if healthy young men got sick, the same chemical would also be unsafe for women and children. It's not really how biology works though, and a few dozen white guys didn't exactly represent all of America. But even though there were a lot of flaws with this experiment, it was the first time somebody thought to test food additives and study them one at a time. Later research that was actually reliable led to almost all of these additives being banned from food, except for sodium benzoate, which is a common preservative in acidic foods like orange juice and soda. But we only use it because we've tested it and it's considered safe. And journalists loved covering the happenings in the DC lab kitchen, so people across the country started thinking seriously about the things that might be used to preserve their food. In 1906, partly because of the public's new awareness, Congress passed the Pure Food and Drug Act, a precursor to today's more rigorous regulations. Those concerns also led to the creation of the FDA, which is the organization that makes sure the ingredients in your food aren't gonna kill you. For the most part anyway. If you decide to crack open 10,000 cans of baked beans, there's not much they can do to help. That one's on you. Since Wiley was so instrumental in protecting America's food, he's often called the father of the agency. So the poison squads were a really horrible idea and full of sketchy science. But because of the progress we've made since then, going to the supermarket today is a whole lot safer.
Thanks to the Poison Squad and the FDA, you can't buy anything on this list of deadly stuff at the grocery store. What a win. After all, when people tell each other about the dangerous stuff out there, our whole species benefits. So send this video to a friend for the health and safety of humanity, or just because you liked it.